Why don't we, do you want to move down a little and we can get started? So thank you, Alexandra. Thank you, Steffi, and everyone for coming here. Biofabrication. While we're here about the future of health and digital and a lot of technology, biofabrication is not what I actually thought it really was. So I'm not sure if any of you really knew what it was. So I will help you in understanding what I've come to understand, spending time with these guys and doing some research, is it's really using materials, or actually growing materials using organisms. And that manufacturing really starts with life. So you heard a little bit about each of what these guys are doing, and here comes Suzanne, which is great. We have Ginger, who is really coming up with a solution in a very sustainable way. Everybody is doing that, but using bricks, and Peter using beef, and then we have Suzanne using leather. So I'm going to ask them each to give you a little bit of a description of what they're doing and what their company's doing, and then we'll start talking a little bit more about how it relates to our lives and in this life. So I think you can look at this as our futures sci-fi panel meets really great solutions to where we're going to go for the rest of our life, and have these guys to thank for it.
All right. Well, first of all, what a very interesting group to be discussing biofabrication with. And just a quick story about bioMason, which is the company I founded. We're essentially growing bricks using bacteria. And I'm not from the scientific industry at all. I actually started off as an architect, and saw a real need for materials to be manufactured in a very different way. I was astounded first to find out that we produce over 1.23 trillion bricks every year. And because of the fuels used in the fossil or the firing process, that's 800 million tons of carbon emissions. And just to put that in perspective, that's more pollution than all the airplanes in the world combined every year. And that's just coming from one simple building material, which is a brick. So what we set out to do is we decided, look at how nature is able to make these hard, sustainable, and durable materials in nature, and how can we learn from that and actually be able to implement that? But not just implementing it so that we can manufacture one in the lab, but really making a viable alternative. So I brought a sample here, and this is grown in ambient temperatures without any fossil fuels, and it took 2 days. So.
Okay, and we'll get back to how each one of these solutions can help in the real world today. So, Peter?
Thank you. Well, what we do is produce meat, basically, for human consumption from stem cells. So it kind of relates to a couple of the talks that we heard yesterday. We use stem cells from muscle tissue, proliferate them, and then basically tell them to become a muscle or meat. Why are we doing this? Well, our main driver is actually not so much a commercial one, but it's more meat business as it is today. Because the production of meat today, and we eat about 300 billion kilos of meat every year on this planet, is actually a pretty big problem, apart from the fact that it produces a very nice nutrient, because it impacts our ecosystem, it impacts global warming, so we are addressing global warming in this summer version after all. About 20% of global warming is actually caused by the production of meat, which is more than transport. So meat and bricks are the unexpected bad guys, probably, in the case of global warming, that you didn't expect them to be. So this is a main driver for us. And there are many more negative aspects related to the production of meat, fresh water usage, for instance, acid rain. So something needs to be done, because consumption of meat is only expected to go up in the next decades. Actually, in 2050, it'll be 50% higher than it is today, due to increasing wealth, due to the increasing population of the world. So something needs to be done. And one of the ways out, we think, is producing meat from stem cells without any of those negative impacts that I just mentioned, or let's say, strongly reduced negative impacts, as I just mentioned.
Fantastic. Suzanne?
Sure. Sorry for arriving a little late. So like Ginger, I'm actually a fashion designer by training. I'm not a scientist. And I really arrived at this world by meeting a biologist when I was researching the future of the fashion textile industry and asking the question, what might we be wearing in 50 years' time? How else might we create a garment? How might we think about design and manufacture? And this was a conversation I had about 12 years ago, and he said to me, well, rather than think about growing a plant like cotton in a field, you might think about putting a bacteria in a vat of liquid and fermenting a garment into a three-dimensional shape. And really, this idea that a bacteria could be a factory that could produce a material for us was quite mind-blowing as a designer. And this idea that you could fabricate something from the bottom up, that you could actually design a product by engineering all the properties that you want into it and allow it to grow into the form that you determine was just quite an extraordinary notion to me as a designer. So, you know, a long time ago, we started to collaborate to think about how we could use a living organism like yeast and bacteria to produce materials for us. More recently, that led to me joining a company called Modern Meadow. And Modern Meadow, similar to Peter's group, are aiming to produce materials, animal products, really without killing the animal. So we have two programs. One is food, and the other is materials. You could, in a very narrow sense, describe that as meat and leather, but in fact, our growing understanding of what this means to fabricate something biologically is that we have a new generation of natural material possibilities, where at one extreme we start with something which is biomimetic, which looks, feels, and smells like leather, but at the other extreme could be a very highly engineered biomaterial with new aesthetic and performance properties. And the same for food. So in a very narrow sense, you might think about that as meat, but what we're beginning to learn in association with R&D chefs is that we are able to grow a very pure form of protein that could be then shaped into different types of food product. So we're just at the beginning of exploring what this new landscape of food and materials can deliver.
And that brings me to my question for Peter first. Would you bring us through the process of how you're working with your beef? And then more importantly, I think the question on everyone's mind is going to be, tell us how it tastes.
Yes, well, the process, in short, is that we take a biopsy from an animal. Theoretically, it could be any animal, but we're talking about beef now, so a cow. From that biopsy, you can isolate the so-called adult stem cells. Actually, yesterday there was a talk about this type of stem cells, so you're all aware of what that is. And these stem cells are there in the muscle to help you when you have a problem, when you have a wound. So they are not muscle cells. They are not differentiated yet, as it's called, but once you have a wound, they sort of sense that, they proliferate, and they repair the wound by forming muscle tissue. And that is the property that we use. So we take those cells, we proliferate them in a bioreactor, and once we have enough biomass, we tell them to become a muscle.
How long is that process?
It takes, all in all, 3 to 4 weeks for a whole run. So, one of the factors that determines feasibility, economical feasibility, is the amount of divisions that you can have that cell make. So there's a lot of work to be done yet. We're not there yet, but this is basically what we do. And this is basically what we did when, some of you might remember that in 2013 a hamburger was shown and prepared in London. That hamburger consisted of 20,000 individual small muscle fibers. And all these 20,000 fibers were individually made in a petri dish. And you can imagine that took quite some time.
Well, you just mentioned you wait until you get to critical mass.
Yeah.
Was that just for the one hamburger patty?
This was just for the one hamburger patty, yes. Yes, so it was quite a costly hamburger. But we did it to show a proof of concept. But having said that, it only consisted of muscle fibers, so only the protein bit of the muscle. No fat, no connective tissue, no blood or myoglobin, as it's called, that is present in muscle, that give its muscle its taste. And fat is also very important for the taste. So to touch on your question about the taste, it's neutral.
So you actually cooked it?
Today it is neutral, but we are now in a follow-up stage where we're producing the fat, producing the connective tissue, doing co-culturing, as it's called. So our next step is taking the step from muscle fiber to meat.
And do you see us eating a burger from you in the next 2 years, 3 years? How futuristic, how far out is this?
We have a plan, obviously, and we think that minced meat should be ready for upscaling within 5 years.
So we're going to have tacos and shepherd's pie before burgers?
If it's minced, you can do anything with it you like. You can make a sausage, you can make a burger. But I specifically say minced because making a bigger piece of meat, like a steak, is much more tricky. Because you need nutrients to go to the core of the product. You need the waste to go out. And we have blood vessels to do that, and they are not yet present in cultured meat.
Terrific. I'm going to move on to Ginger because you're doing something that I think is not only sustainable, but something that's needed and can be used not only in developed countries, but developing countries, and really can offer solutions to many of us in terms of how we want to live in sort of this eco-friendly world. So maybe you could walk us through the process of the bricks that you're making, and also how realistic for the process and the different materials that you use and where we could apply this.
Yeah, so I guess for looking at how do you grow a brick, I think the biggest star of this are the trillions of tiny workers, meaning the bacteria that's used. So I guess similar to what Peter is describing, we start with a fermentation. And this particular type of organism, it's found in a marine environment. It's very similar to some of the same organisms that enable coral reefs to form. So really what the organism is actually doing is it's creating an environment for calcium carbonate to form. And so what we do is we take sand or aggregate pieces. Sand is clearly one of the most abundant materials, but this sand acts as a matrix. And so the sand is placed in a mold, and the mold is then inoculated, so to speak, with the bacteria, so it becomes almost like a bioreactor in and of itself. And instead of, allowing the material to cure through perhaps a kiln or drying, we grow it using an aqueous solution. So what's really interesting to us as we've gone through, this path of scaling and economies of scale is really looking at how other industries relate to what it is that we're doing. And what we found is that hydroponics is one of the closest related fields. So if you imagine what a factory would look like that grows bricks, it looks a lot like a greenhouse, or it looks a lot like a field, depending on the conditions in which you're trying to manufacture material.
Would you share a little bit about, when you say aqueous, your options that are out there? Because that's pretty fascinating.
Yeah. So, what we're doing is we're delivering nutrients and required calcium sources for the microorganism to propagate. And so the carrier for that is an aqueous solution. And what we found is that different types of water work quite well for us. So, you can imagine in the lab, you start with, the purest of pure waters. And then we started to go down to see what's the dirtiest water we can actually use for this process. And what we found was that the dirtier the water became, the more nutrients, the more environments were able for the microorganism to propagate even further. So in our systems, we've used gray water, we've used seawater. There's certainly different characteristics that has, but what it told us in terms of viability and in terms of going into developing countries is that, one of the biggest threats that we have right now is fresh water. And I certainly wouldn't want to be in that decision over should I build a house out of concrete or should I have drinking water. So one of the things that we wanted to do early on was see, what are the possible waste streams that we could use? And I'm very excited about wastewater because I think that, in a really, maybe not too far out, but if you could imagine that bricks are a byproduct of making clean drinking water. That would be, a tremendous goal for us.
And really everyone would benefit. Just show everyone that for another minute. What kind of sand did you use for this one?
So this sand is actually a waste mine fine. It comes from a granite quarry, so granite that's produced for roads, et cetera. And this is really the stuff that's left over that's not sellable. It's more of the fines, more of a mix of different grades. And prior to starting the company, I actually lived in the Middle East for a while, and I was astounded to see all the sand and looking at how the sand there is a incredible natural resource that can be used for making materials directly on site simply by inoculating the sand with a bacteria. So other aspects of the material questions that come up are the color. So the color for us comes directly from the aggregate that's used. So if you use desert sand that has, a nice tawny brown, you would have a nice tawny brown brick. This looks a lot like the virgin granite that it was made of.
Fantastic. All right, great. Suzanne, fashion designer, over to using, materials or bacteria, however you're growing leather. How realistic is this, and how does that process work? And will I soon be sitting up here wearing something that you've not only designed but grown for me?
Well, that's the intention. That's the hope. Absolutely. We use the same kind of cells that Peter uses in meat for the leather. We would take the skin tissue and really grow the pure dermis layer of the skin without the fat, without the hair of the animal, obviously, which environmentally, the tanning process and the toxicity of the chemicals, in order to strip out the hair and the fat is a large part of what makes the leather industry so toxic.
Well, walk us through a little bit also with how you put it in, you put scaffolding around it and you really get it to grow, or where you've taken it so far.
So there are different ways that you could approach the construction of the material. Our scientific founders actually pioneered bioprinting, and they were bioprinting human tissue. So actually studying growing lung tissue and skin tissue, but for pharmaceutical testing and towards regenerative medicine. So we started out by taking that same approach to scaffoldless tissue engineering for materials. So that would be one approach. Another would be using a scaffold, possibly. So that would be that you seed the cells on another structure and you allow them to populate that structure and then to grow into the form that you choose. It's really a journey for us. This is, with biotech research, it's not something that happens in 6 months. It's over a number of years. In terms of when it's going to hit the market, I think, initially it will be something that enters very much at the high end, just because of we need to go after the high-value product first. And then, with economies of scale, we can get to something which actually starts to have, greater impact. But for us, we're probably thinking it's, between maybe 2 to 3 years to 10 years, depending on where in the market we hope to hit.
Well, you mentioned Modern Meadow has also two products, in essence, or 2 areas that you're focused on.
Yeah.
So how does that all play into the leather that you're producing?
Our strategy really is to focus on materials in the short term. So we have a food program, but most of our resources are directed at the materials. And it's because we've had such huge interest, really, from industry. The sustainability possibilities around this are huge. There is a global leather shortage. People are concerned about where the materials are coming from and how the animal's treated. Every step of the supply chain is complex. There isn't enough of the material, and so the global demand is going up. If you're growing a material in a laboratory, then you're not constrained by shape of the animal, right? So you can grow something, by the meter on a roll, ultimately.
How do you see that? Explain that, because I know I asked you that question yesterday, and you said, "Oh, we'll grow it as big as this room," and I'm imagining a small petri dish.
It depends on the ultimate technique that we end up using to scale. But this is the thing that is most interesting to a lot of brands, is that you could grow either something into the shape you want, so there's zero waste potentially. We might get to the point where you could actually grow something into a 3-dimensional shape. So instead of needing to go from 2D into 3D, you grow directly into 3D. All of those things are possible. It's just a case of, where we choose to go first.
Another question, I think, for all of you, and we can start maybe with you first, is what is the business model? Because you're all funded, or you all may be continuing to look for funding, which seems to be out there, so I'm not worried about that for any of you. But then what is that business model?
At the moment, we are looking to partner with just 1 or 2 brands that we would, take the product to market with. It's difficult for us to say too much because of the stage that we're at. And really, it's about how we find the most efficient way to scale it, to deliver it at the right price. And
that will be through, you're based in Brooklyn?
We're based
New
in
York?
Brooklyn. We have we're still at R&D scale, so we're not yet at pilot, although we have the space there to turn it into a pilot plant. It may well be that, if we work with a brand partner, that they actually, it might be licensed, it might be a JVA, it might be that, the product is produced locally rather than shipped. Those kinds of things are possible. Urban manufacture would totally be possible.
Very sci-fi. So, Peter, for you, I think you're not yet in a pilot. I think Ginger's in a pilot. So,
no.
Where are you?
We have our thoughts about the business model. We're definitely going to seek partnering in some of the relevant areas for us that are just too important and too big for us to invent ourselves. An example of that is the feed that you give to the cells, or the feed, the nutrients that you give to the cells, or the feed as it's called when you produce a live animal. Because that's highly impacting the cost of the material. So reducing the cost of the nutrients is a big one for us for the future.
How do you do that?
Scaling it up and finding the right sources, probably different ones from today, because the nutrients that are used to grow cells are made from a medical point of view today, and cost in that case is, let's say, less of an item than it is for us, because we need to be competitive in the end, obviously, with natural meat. So you do that mainly by finding the right sources. Think about algae, or think about certain types of bacteria that can be the source of the feed for the cells. Having done that, we're mainly a research-oriented company, or we will be. We're in the startup phase, as you said. Our plan is not to become a giant meat producer, so we will probably license the knowledge that we have all over the place. And that means that we somehow have to protect the knowledge that we gain in the next couple of years. So that's an important issue for us as well.
Do you foresee, you started with cattle, but could you see replicating this to chicken, poultry,
It is.
fish?
You know, when your imagination starts going, it goes all over the place. Yeah, it's true. You can do anything. You can make a giraffe. You can make Justin Bieber. You can do whatever you want. Yeah, without killing him.
Okay. Ginger, I don't know how you follow that one up, but I think you're in pilot mode.
Sounds like a fun birthday party thing. But yeah, so our business model, when we first started out, we recognized the scale and the impact that a material like this could have for all different types of places on a global scale. So we set out to make this as easy as possible for others to make. So essentially putting it into the hands of existing manufacturers who have proven distribution channel, they have market adoption, they have manufacturing and scaling capability. So the question early on became, the packaging of the microorganism and the constituents as a way that we could just be able to add water to the process so that it can be easily adopted into current industry manufacturing. So we, as well, have a licensing model, but, there's also, I think of it kind of like an HP printer and ink, is that we've gone through this pilot, scale, which has been quite rewarding and quite interesting to go through, to take a material that, you can grow one at a time, and then you're seeing 500 of them come off every few days. And that's, clearly we need to be able to make millions of them at a time. But for us at a pilot scale, we're able to, in a way, be the first customer of ourselves. So if, things need to be changed, or you go through and learn the economies of scale, or just one simple change in automation, you're learning a lot about how to make it easier for someone else to make. So one of the other models that we have is that we recognize that, well, if you don't need a kiln to fire the bricks, you really don't need that much, except for a pump, mixing system, and then a delivery system for this liquid solution. So that's when we really started to think, what if we could grow the bricks directly on site, directly onto a construction site, so to speak. And what's interesting about that is that there's a lot of CO2 that's produced by the manufacturing of traditional cementitious and clay materials, but something else is quite astounding is the transportation. So there's a significant amount of additional CO2 just from that. But, let's talk about the pain points of the customers and look at how much of their selling price cost is actually in the transportation cost that it takes to be able to bundle these materials up and ship them directly to site. So we're looking at solving, helping solve some of the pain points and problems that existing masonry manufacturers have, which is A, looking at fuel shortages and fuel increase, and B, looking at transportation cost, and then C, ultimately labor cost that's attributed to the price of a brick. And then other materials as well. And I guess just to speak a little bit further about bioMason itself, is that we started off with a brick. It's certainly death by units. It's making consistent product time and time again. The bricks have to all be the same, but we are equally just as curious and astounded every day at what else can we make with this. So what we realize is that it is a binder technology. So bricks are just the beginning. I mean, there are other materials and other construction products out there that have cementitious binders that we've been exploring on. What else can this go into, and what else can we help to make an impact with?
So we have a few minutes left. I think it would be really interesting to hear from each of you what the challenges were that you faced and are facing going forward, because you are the future of manufacturing. It's really, truly disruptive. It's not 3D printing, as we all have now heard. So maybe you can share some of your thoughts on that.
I mean, I think what's interesting is really biofabrication was a field that was really started out in a biomedical context where, biology was we were looking at growing, tissues for implantation in the human body. And so that's really the original definition of biofabrication. And what we're all exploring is something that goes into a consumer or an industrial context. And the challenge there is to take biology and make it scalable to the point where it can be commercially viable. And I would say that scalability of the biological process and the speed at which you can grow something are going to be the things that really challenge us.
Peter?
Yeah, it's kind of the same for us, I guess. First of all, we see, let's say, a scientific challenge. So just making it happen and making it commercially viable. And I'm sure it will at some point. I'm really convinced it will at some point, but there is no exact way to tell when. I mean, it might last 5 years, as I said, and I'm pretty optimistic that it will. But you never know what's going to happen on the way there. So that is a challenge, just the research stuff.
Well, being based in the Netherlands versus being based in the U.S., do you see that as an advantage to you, or?
Not necessarily, although we are based in a region that is very promotional for biotech setups and startups. So in that sense, I can't complain.
Okay.
So. And another challenge for us, if I might add one, we're talking about meat, and meat is a very emotional product. I mean, it touches a couple of nerves in our brain that you can't mess with. It's in that sense, it's completely different from most other nutrients that we have in our diet, I guess. So people want meat to be natural. They want meat to be of a known origin, preferably. In many cases, it is not, I can tell you, but meat is a touchy subject. So consumer acceptance of this product, replacing a product like meat with something that comes out of a lab, between brackets, that'll be a tricky thing.
Yeah, will it still be, could it be vegan meat since it comes out of a lab? But no, because the origins are truly
I always say we use the same genetic information to produce the same product. So yeah, I don't know why we couldn't call it meat. It'll have to be treated as a novel product and get its legal stuff accepted.
That should be our next panel session when we all get together again.
So there is some legal stuff attached to it, but in the end, it is meat. Yes, it's just meat.
Okay, Ginger, you want to have?
Yeah. In terms of challenges, I mean, I completely agree. And what I think that I'm hearing definitely from everyone here too is that we're looking at large scale commodity driven products. So, starting off with the lowest hanging fruit, starting off with, the high end, starting off with really fundamentally understanding, how materials are grown, it takes time. And I think that the challenge that we've had is, certainly time and scaling and really looking at, what is the, less clean environment we can use to be able to do this, because we knew early on if a brick masonry company is not going to be wearing, a lab coat, and they're certainly not going to have a clean room. So, challenges of things like contamination and being able to solve your way out of these problems with science, certainly very interesting challenges that we've had, but and fortunately those are solved. I mean, there are other challenges that we'll have definitely down the road with that as we start to distribute it out, but one last, I guess, thought on the challenges, and I personally embrace it, is that, bricks have been around for thousands of years, and Portland cement has been around over 200 years, and biomason's been around a little over 2 years. So there's plenty to learn, and there's a lot of new challenges that we'll embrace, but, that certainly it's a beginning to understanding what it means to grow a material, to start with a living product, and what it means for manufacturing with that.
Great. Well, thank you all. This is fascinating.
Thank you.